Welcome to the Curious Voyager. It's lovely to have you here tonight. Wherever you are right now, a bed with the blanket pulled up to your chin, a couch with one lamp still glowing in the corner, a train sliding through the dark, a room where the day has finally gone quiet, I'm glad you found your way here. Settle in. Let your shoulders drop a little. There's nothing you need to do for the next while except breathe and drift and let a strange and beautiful story wash over you slowly. And I'm curious, where in the world are you listening from tonight? What time is it in your corner of the night? Somewhere it's just past midnight and the streetlights are humming. Somewhere it's the small, soft hours before dawn. Somewhere it's an ordinary evening and you're simply tired down to your bones. Wherever you are, whatever the hour, you're welcome here. If you enjoy these slow, wandering journeys and you'd like more of them, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that quiet kindness more than you'd think. And to those of you already subscribed, already part of this, thank you. Truly, you're the reason there's a next journey at all. Now, before we begin, let me tell you the only rule of this place. There isn't really one. You don't have to follow every twist. You don't have to remember a single name or number. If you drift off somewhere in the middle, that's not a failure. That's the whole point. The story will still be here when you wake, patient as ever, and you can find your way back to it another night. I'll try not to make this so interesting it keeps you awake, but if it does, well, at least you'll have learned something. A fair trade, I think. So, let's begin, shall we? Softly, one small mystery at a time. Tonight I want to tell you about a shape. A shape so strange that the textbooks called it impossible. Not unlikely, not rare. Impossible the way the books might say you can't have a square with 3 sides or a triangle with a curve for an edge. A shape that the rules of nature, as we understood them for the better part of a century, simply did not allow to exist inside a solid piece of matter. And I want to tell you about the man who found it anyway, and the years of laughter he had to walk through, and the tiny grain of it that turned out to be older than the earth itself, hidden in a museum drawer in Italy after a journey of 4.5 billion years. But all of that is later. Let's start where the story actually starts. On a single, ordinary morning, it's the 8th of April, 1982, a Thursday. The place is a laboratory at the National Bureau of Standards in a town called Gaithersburg in Maryland in the United States. The National Bureau of Standards, you might know it better by the name it goes by now, the National Institute of Standards and Technology, or NIST. But back then it was still the Bureau of Standards, and it was exactly the kind of place the name suggests. A place of measurement. A place where people decided very carefully how long a meter really is, and how heavy a kilogram truly weighs, and what counts as correct. A temple of getting things right. And working there, on a sabbatical away from his home institution, the Technion, in Israel, was a materials scientist named Shechtman. Daniel Shechtman. A quiet, meticulous man who studied metals for a living. That's what a materials scientist does, more or less. They look very, very closely at what things are made of. What happens inside a piece of aluminum when it cools? Why one alloy is strong and another crumbles? The hidden architecture of ordinary stuff, a spoon, a wing, a wire, the arrangement of the atoms you'd never see with your naked eye in 1,000 lifetimes. On that morning, Shechtman was studying a particular metal he had made himself. It was an alloy, a blend of 2 metals melted together, of aluminum and manganese. Aluminum, the light silvery stuff of drink cans and foil. Manganese, a harder, grayer metal you've probably never held in your hand, but which quietly hardens the steel in a great many things around you. He'd mixed them, melted them, and then he'd done something rather violent to them. He'd cooled the molten metal astonishingly fast. So fast the atoms barely had time to move. There's a technique for this, and it has a lovely name, rapid solidification, sometimes done by a method called melt spinning, where a thin ribbon of molten metal is flung against a spinning cold wheel and frozen almost instantly. Imagine pouring honey onto a plate that has somehow been chilled to the temperature of deep space. The honey wouldn't spread and settle the way honey likes to. It would seize up mid-motion, caught in the very act of pouring. That's the idea. You freeze the metal so quickly that its atoms are trapped wherever they happen to be, before they can arrange themselves into their usual tidy patterns. Metallurgists do this to make unusual materials, to catch the metal in a strange, hurried, in-between state, and see what it becomes. So Shechtman had this hurriedly frozen ribbon of aluminum and manganese, and he wanted to look inside it. Not with his eyes, you can't see an atom with your eyes. Atoms are far too small. He used an instrument called a transmission electron microscope. Now, that's a mouthful, so let me slow down and unpack it, because it matters for what he saw. A transmission electron microscope. An ordinary microscope, the kind you might remember from a school classroom, shines light through a thing and lets you see it bigger. But light is too clumsy, too broad-shouldered to show you something as tiny as an atom. So instead of light, this machine uses a beam of electrons, tiny particles, far, far smaller than a ray of light, small enough to feel their way around the atomic world. The beam passes right through a wafer-thin slice of the metal. Transmission, it transmits, it sends the beam through rather than bouncing it off the surface. And on the other side, the electrons that have passed through carry a message about what they met on the way. Here's the part that matters, and I'll say it gently, because it's the whole heart of the thing. When that beam of electrons passes through an orderly arrangement of atoms, rows and ranks of them, lined up neat and regular like an orchard seen from above, like soldiers on parade, like the perfect grid of an egg carton, the beam doesn't just pass straight through, it scatters. It bends off the atoms in specific directions, and only in those directions. The way ripples in a pond will pass through a row of evenly spaced posts and come out the other side, reinforced along certain lines and cancelled along others. The electrons that come through land on a screen or a photographic plate, and they leave behind a pattern of bright spots. This is called a diffraction pattern. And a diffraction pattern is a kind of fingerprint. It's the atoms telling on themselves. If you know how to read it, and Shechtman knew how to read it as well as almost anyone alive, the arrangement of those bright spots tells you the arrangement of the atoms inside. The spacing of the spots tells you the spacing of the atoms. And, crucially for tonight's story, the symmetry of the spots tells you the symmetry of the atoms. If the atoms are arranged in a pattern with fourfold symmetry, a pattern that looks the same when you turn it a quarter of the way around, like a square, then the bright spots will also come in fours. Turn the pattern, and it repeats. The picture on the plate is a faithful little portrait of the order hidden inside the metal. So Shechtman slid his rapidly frozen aluminum-manganese into the microscope. He fired the electron beam through it, and he looked at the pattern of bright spots that came out. And he stopped, because arranged before him in a perfect ring were 10 bright points, 10 of them, spaced with flawless evenness around a circle. like the 10 numbers on a clock face, if you took away the 11 and 12 and 1 and 2 and spread the rest out just so. 10 sharp, brilliant, unmistakable spots. A pattern with 10-fold symmetry. A pattern that would look exactly the same if you rotated it by 1/10 of a full turn. Now to you and me, 10 evenly spaced dots in a ring sounds pretty, harmless, rather elegant even, but to Dan Shechtman, staring at that plate on that April morning, 10 spots in a perfect ring were not pretty. They were impossible. They were a thing that could not be. It was as though he'd measured a room and found it was wider on the inside than the outside, as though he'd counted the coins in his hand twice and got a different number each time. The pattern in front of him was saying something about the atoms inside that metal, that the deepest, most settled laws of his entire field insisted could never, ever be true. He did what any careful person does when the world stops making sense. He counted again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots. He counted a third time, still 10. He rotated the sample, tilted it, checked it from another angle, ruled out the small betrayals a microscope can commit, a flaw in the lens, a trick of the light, a smudge, a double image, the machine playing games. None of it. The pattern held. It was real, and it was reproducible, and it was 10. He reached for his laboratory notebook, the plain, lined book every scientist keeps at the bench, where you write down what you did and what you saw, in the moment, in pencil, so the truth is preserved before your memory can soften it. And in that notebook, on the page, for that day, Dan Shechtman wrote 3 characters that have since become quietly famous among the people who love this story. He wrote 10-fold. And then, after it, 3 question marks. 10-fold, question mark, question mark, question mark, 3 question marks. Think about that for a moment. This was one of the most skilled electron microscopists in the world. He knew precisely what he was looking at. He knew exactly what 10-fold symmetry meant and exactly why it wasn't allowed. And still, faced with the thing itself, sitting bright and calm and undeniable on the plate in front of him, the only honest thing to write was 3 question marks. Not a triumphant note, not Eureka, just a man doubting his own eyes, in ink, and being brave enough to leave the doubt on the page. And he said something to himself, quietly, in Hebrew. He said, Ein hayakazo. There is no such creature. There is no such animal. The way you might say if someone told you they'd seen a fish walking down the street wearing a little hat. That's not a thing. That doesn't exist. There is no such creature. And yet here it was, 10-legged and calm, staring back at him through the microscope. I love that line, there is no such creature, because it captures the exact feeling of standing at the edge of something new, the mind refusing, even as the eyes insist. Hold on to it. We'll come back to it more than once tonight. Now let it settle a moment. You in your bed, the metal on its plate, the 10 spots in their ring. Nothing is resolved yet. A careful man has seen an impossible thing and written down his doubt. That's where we are. No rush. We have all night, and the ideas will keep. Let me pour you a little more of the strangeness, slowly, because you can't feel how astonishing those 10 spots were until you understand why they weren't allowed. And to understand that, we have to go back before that April morning. Back through about 70 years of settled, confident, textbook solid science. We have to visit the tidy world that Shechtman's photograph was about to quietly break. So let's build that tidy world first, gently the way it stood. For a very long time, generations of scientists, whole careers, whole libraries of textbooks, there was a word. And the word was crystal. And everyone was quite sure they knew what it meant. When you hear crystal, you might picture a quartz point, or a snowflake, or a diamond, or the salt in the little grinder on your kitchen table, and you'd be right, those are all crystals. But to a scientist, a crystal wasn't really about being clear, or sparkly, or precious. A crystal was about order. Specifically, a certain kind of order, the repeating kind. Here is the picture that lived at the center of crystallography for the better part of a century. A crystal is a solid in which the atoms are arranged in a pattern that repeats over and over. Endlessly, the same little cluster of atoms, call it a building block, a unit cell, a single tile in an infinite mosaic, copied and pasted in every direction, again and again, filling up space without any gaps and without any overlaps. Like bricks in a wall, all identical, all laid in the same rhythm, like the squares on a chessboard marching off to the horizon. Like a wallpaper pattern that goes on forever. Take one step in any direction, and if you take exactly the right size step, you arrive at a spot that looks precisely, exactly the same as where you started. Same atoms. Same arrangement. Same view. That's the essence of it. A crystal repeats. This wasn't a guess, and it wasn't a fashion. It was the bedrock. For roughly 70 years, all of crystallography rested on a single quiet assumption, so obvious that hardly anyone bothered to say it out loud. An ordered solid must be a repeating solid. If the atoms are arranged in a sharp, definite, long-range order, the kind of order that gives you those clean, bright diffraction spots, then that order must come from a pattern that repeats. Order meant repetition. Repetition meant order. The two were welded together so tightly in everyone's mind that they were treated as the same single thing. You could not, people believed, have one without the other. To have order was to repeat. To repeat was the only way to be ordered. And out of that assumption came a rule. A hard, proven, mathematical rule, not a hunch, not a rule of thumb, but a theorem. The kind of thing you can demonstrate with pure geometry and never wriggle out of. It's called the crystallographic restriction theorem, a grand name. But the idea underneath it is something you already understand in your bones, and I can show it to you with nothing but a floor and some tiles. Picture a floor you want to cover completely with tiles. No gaps, no overlaps, every bit of the floor covered, and all your tiles the same shape. Now, which shapes will work? Squares work. Of course they do, think of any bathroom floor. Lay squares edge to edge, and they fill the plane forever, 4 of them meeting neatly at every corner. Squares have fourfold symmetry, turn a square a quarter turn and it looks the same, and they tile a floor perfectly. Triangles work. Equilateral triangles, all sides equal, fit together snugly, 6 of them meeting at each point, covering everything. Threefold symmetry, and it tiles. Hexagons work, 6-sided shapes, like the cells of a honeycomb. That's exactly why bees build with them. Hexagons packed together with no wasted space at all, 3 of them meeting at every junction. 6-fold symmetry, and it tiles beautifully. Nature figured that one out long before we did. And you can make a floor from simple parallelograms and rectangles too, 2-fold shapes, 1-fold shapes. Those all work. But now, try a pentagon. A regular 5-sided shape, all sides equal, all angles equal, the shape of a starfish's outline, or a home plate on a baseball field, or the little cells on the surface of a soccer ball. Try to tile a floor with pentagons. Go on. Lay one down, then fit another against its edge, then another around the point where they meet. You can't do it. It simply will not close up. Fit 3 regular pentagons around a single point, and you'll find an ugly wedge of empty floor left over, a gap, a slice of nothing that no pentagon can fill. Fit them another way, and they'll start to overlap, climbing over each other, refusing to lie flat. No matter how you turn them, how you nudge them, how patient you are, regular pentagons will not tile a floor. They always leave gaps. There's a stubborn little wedge of leftover space that the five-fold shape can never account for. Anyone who's ever tried to arrange five-sided things neatly has felt it, that faint geometric frustration, the shape that won't behave. This is the pentagon problem. And it's not an accident or a lack of cleverness on our part. It's baked into the geometry of flat space. Five-fold symmetry and a gap-free repeating pattern simply cannot coexist. The angles don't add up. The arithmetic forbids it. And the crystallographic restriction theorem is really just the grown-up, rigorous version of that floor-tiling truth, applied to atoms instead of tiles. If a crystal is a repeating pattern that fills space with no gaps, and everyone was certain that's exactly what a crystal is, then its symmetry is limited to the same short, exclusive list of shapes that will tile a floor. A repeating crystal can have one-fold symmetry, or two-fold, or three-fold, or four-fold, or six-fold. And that is the entire list. Those 5 numbers. 1, 2, 3, 4, 6. Notice what's missing. There's no 5. There's no 7, no 8. And there's no 10. 5-fold symmetry is forbidden. 10-fold symmetry is forbidden, not rare, not difficult, not waiting for a clever enough chemist to coax it into being. Forbidden, ruled out by the same unbending geometry that keeps the pentagons from tiling your floor. A repeating, orderly solid could no more have 10-fold symmetry than you could pave a patio with starfish and leave no gaps. So now, perhaps, you can begin to feel the weight of what Shechtman was staring at. 10 bright spots in a perfect ring. 10-fold symmetry, plain as day, sharp and bright and undeniable, the fingerprint of an atomic arrangement with a 5-fold, 10-fold order at its heart. And every crystallographer alive had been taught, correctly, provably, from the geometry up, that such a thing could not exist inside a solid. The diffraction pattern he was holding was not merely surprising. It was, by the accepted laws of the field, a logical impossibility. It was a photograph of something that the mathematics said could not have a photograph, because it could not have a self. That's why the 3 question marks. That's why there is no such creature. A lesser understanding might have felt only mild surprise, but Shechtman understood exactly and precisely how impossible the thing in front of him was, and that understanding is what made the moment so vertiginous. The better you knew the rules, the more the plate seemed to break them. Because here's the exquisite trap he was caught in, and I want to lay it out slowly, because it's the pivot the whole night turns on. Those sharp, bright, discrete spots, the very fact that they were sharp and bright and discrete, that was the unmistakable signature of long-range order. A messy, disordered solid, one where the atoms are jumbled every which way like a heap of sand, doesn't give you crisp spots at all. It gives you smears, blurs, vague halos of nothing in particular. Sharp spots mean order. Sharp spots mean the atoms are arranged with real, long-reaching, disciplined regularity, coordinated over vast distances on the atomic scale. There was no doubt at all that this metal was deeply, profoundly ordered. And yet its order had a symmetry that order was forbidden to have. Long-range order right there in the sharpness of the spots, and 10-fold symmetry right there in their arrangement. Two things that, according to 70 years of settled science, could not possibly appear in the same photograph. Order that could not be. It was as if he'd found a married bachelor. A four-sided triangle, a word that meant its own opposite. Both halves of the contradiction were staring at him at once, and both were undeniable, and there was no room in the accepted world for both to be true. So one of two things had to give. Either something was wrong with the experiment, the sample was flawed, the microscope was lying, Shechtman had made some subtle error and fooled himself, or something was wrong with the textbook. Wrong with a rule that had stood for the better part of a century. Wrong with the very definition of what a crystal was allowed to be. There was no comfortable third option. Either the camera was lying, or the law was. And I'll be honest with you, softly, from the warm safety of tonight, with the whole story already knowing how it ends. In that moment, in April of 1982, standing alone at the microscope, there was no way for Dan Shechtman to know which it was. He couldn't see the future. He couldn't know that this quiet, careful morning would one day be called the beginning of a scientific revolution. He couldn't know about the Nobel Prize waiting nearly 30 years down the road, or the ancient grain of the same impossible stuff sleeping in a museum drawer in Florence, or the 4.5 billion-year journey it had taken to get there. All of that was hidden from him. All he had was 10 spots in a ring, 3 question marks, and a growing, uncomfortable certainty that he had not made a mistake. He counted them again. 10. He had not made a mistake. Which meant, and this is the thought that must have arrived slowly and coldly and thrillingly in the quiet of that laboratory, which meant that the textbook was wrong, or at least that the textbook was incomplete. That somewhere in the tidy, settled 70-year-old assumption that order must mean repetition, there was a hidden crack. A thing everyone had believed and taught and built their careers upon that simply wasn't the whole truth. And this soft-spoken materials scientist on sabbatical, far from home, had just walked straight into the crack and fallen through it. Let that idea sit with you for a moment, because it's a gentle and rather beautiful one to carry towards sleep. A rule that everyone treated as a law of nature, order, requires repetition, turning out to be not a law at all, but only a habit of thought. A limit not in the world, but in our imagination of the world. The universe, it would turn out, had never actually agreed to that rule. The universe was perfectly capable of building order without repetition. It had simply never occurred to us that such a thing could be, and so we had written our impossibility into the textbooks and mistaken it for the impossibility of nature. But of course, no one knew that yet. On that April morning, all anyone would have seen was a diffraction pattern that shouldn't exist, and a man who wouldn't stop insisting it did. You might imagine that a discovery like this would be met with excitement. A door swinging open, colleagues crowding around the plate, eyes wide, someone running to fetch the coffee, and someone else the champagne. That's how we like to picture the great moments of science, the breakthrough greeted with joy. It wasn't like that. Not even a little. What actually waited for Dan Shechtman on the other side of those 10 bright spots was not celebration. It was something much harder and much lonelier. It was disbelief, and then dismissal, and then, for a good long while, something very close to ridicule. Because when you show the world a photograph of something the world knows to be impossible, the world does not usually thank you. The world, more often than not, decides that you must be the one who is mistaken. The problem, you see, wasn't only that the result was strange. Strange results turn up in science all the time, and usually they turn out to be mistakes, a contaminated sample, a miscalibrated machine, a smudge on a lens read as a signal from the stars. 99 times out of 100, when a young or not so young researcher comes running with a photograph of the impossible dissolves under a second, more careful look, and everyone goes back to work. The scientific world had learned, through long and sometimes painful experience, to be deeply skeptical of the extraordinary claim. And there are few claims more extraordinary than I have found a crystal with a symmetry that geometry forbids. So when Shechtman began, cautiously, to show his 10-spotted photograph to the people around him, to the other scientists at the Bureau of Standards, to the ones whose job it was, quite reasonably, to be skeptical, he was not stepping into applause, he was stepping into a wall. The very thoroughness that made him such a good scientist, the care with which he'd ruled out every ordinary explanation, would not be enough. Because the thing he was claiming was not the kind of thing that a photograph, by itself, could make people believe. It asked them to give up something too large. It asked them to give up a rule they'd built their whole understanding upon. And there was one figure still to come in our story, whose voice carried more weight in the world of structural chemistry than almost anyone's, a scientist so decorated, so brilliant, so revered, that when he declared a thing impossible, people simply believed him and moved on. He had not yet entered the tale. But he was coming, and when he did, he would say something about Shechtman and his impossible crystal that would follow the quiet Israeli scientist for years, a single cutting sentence that turned a scientific disagreement into something that felt, for a long and difficult stretch, like a public humiliation. But that's for a little further along the road, and there's no hurry to get there. For now, let it rest where it is. A morning in April. A metal frozen too fast to think. 10 bright points arranged in a ring they had no right to form. A notebook, 3 question marks, and a whispered "there is no such creature." And a man who had just seen, though he could not yet prove it and could not yet convince a single soul, that one of the most settled ideas in all of science had a hole in it, a hole shaped, of all things, like a pentagon that would not tile a floor. The camera was not lying. It would take years and a rescue from an unexpected corner of pure mathematics, and eventually a stubborn refusal to back down in the face of the most famous voice in the field before anyone would agree with him. But the camera was not lying. Rest there a while with that thought. The impossible thing, sitting quietly on its plate, patient as anything, waiting for the world to catch up to it. It had waited, though no one knew this yet, for 4.5 billion years already. It could wait a little longer. So, let us follow Dan Shechtman out of that April morning and into what came next. Because what came next was not a celebration. It was not the quiet satisfaction of a man who finds something unexpected and is immediately believed. That is not how this story goes, and perhaps you already sense that, lying wherever you are tonight, half listening to the dark. Science, at its most human, is not a smooth machine that accepts new things gracefully. It is more like a house built over many generations, with foundations so deep and walls so thick that even when something is wrong, the structure holds itself upright by sheer accumulated weight. And Shechtman had found, on that April morning, something that should not have fit through the door at all. The trouble began almost immediately, and it began quietly, the way real trouble often does. He knew what he had seen. He had counted the spots again and again. He had rotated the sample, re-examined the diffraction pattern from different angles, confirmed that it was stable and real and reproducible and not an artifact of a dusty lens or a miscalibrated instrument. The 10 bright points arranged in their ring were there every time he looked, and the geometry they described, 5-fold, 10-fold symmetry, was geometry that his training and everyone else's training insisted could not belong to a real solid crystal. He started telling people, carefully, hesitantly, as you would if you had just seen something you were not sure you believed yourself. He showed the pattern to colleagues in the lab, and the response he got was not excitement. It was skepticism. Not the gentle, curious skepticism that says, "How interesting, let us investigate further." It was the harder, more uncomfortable kind that says, "You must have made a mistake." His group leader at the National Bureau of Standards reportedly handed him a crystallography textbook, not as a gift, not as a starting point for a conversation, as a suggestion, or perhaps something closer to an instruction, that he go back and reread the parts that explained why what he was claiming could not be true. There is something almost unbearably human about that gesture. A textbook handed across a desk carrying the weight of 70 years of settled science. Here, you have missed something basic. Look again. Shechtman looked again. He had already looked again, many times. The pattern was still there. But the difficulty did not stop at gentle correction. Eventually, and this part is recorded in Shechtman's own recollections, in enough places that it is not a rumour, he was asked to leave his research group. The reason given, as he recounted it, was that he was bringing disgrace on the team. The thing he had found, or thought he had found, was an embarrassment, not a discovery. An error that reflected badly on everyone around it. Think about that for a moment if you can. Not a forced departure for misconduct, not a conflict of personalities, but a departure, reportedly, for the crime of reporting a result that contradicted the established rules too loudly and too persistently. A scientist asked to step away from his colleagues because he would not stop believing what his instrument was telling him. He did not stop. That is the thing about Shechtman that the story, even told briefly, cannot help but reveal. He was not the kind of man who surrendered a data point because it was inconvenient. He had his notebook. He had his images. He had the pattern, repeatable, solid, sitting there on the photographic plate, regardless of what any textbook said about it. And he carried those images with him. For roughly 2 years after that April morning in 1982, his findings sat unpublished. 2 years. Not because he gave up, and not because he had been wrong, but because the path from a diffraction photograph to a paper in a journal runs through other human beings, reviewers, editors, colleagues, and the human beings in that path, almost to a person, were not ready to believe what he was showing them. The idea was too large. The violation it implied was too fundamental. 2 years is a strange kind of silence for a discovery. Imagine carrying something like that, the certainty that you have seen something real, something that reshapes a corner of the physical world, and being unable to convince anyone around you of it. Not because the evidence is weak, because the evidence contradicts what everyone already knows, and what everyone already knows is so deeply embedded that the evidence cannot, by itself, be enough. That silence had a particular texture to it, and the texture was about to get harder. Because it was during this period, and in the years that followed the eventual publication, that the most formidable voice in all of structural chemistry turned its attention to Shechtman's work and declared it wrong. His name was Linus Pauling. You may be drifting now, and that is perfectly fine. Let Pauling's name settle in gently, the way a stone settles into still water. He does not need to jolt you awake. He is, in the context of this story, a figure of genuine and enormous complexity. Not a villain, not a fool, but something more interesting and in some ways more troubling than either. Linus Pauling. At the time, Shechtman was fighting to have his work accepted. Was perhaps the single most decorated scientist alive. He had won the Nobel Prize in Chemistry in 1954 for his work on the nature of the chemical bond, work so foundational that it had reshaped the way chemists thought about the architecture of molecules. And then, separately, he had won the Nobel Peace Prize in 1963 for his activism against nuclear weapons testing. 2 Nobel Prizes in 2 different fields. No one alive had done that. No one since has done it. When Linus Pauling said something about chemistry, the scientific world listened. Not as a courtesy. Because he had earned, over decades, the presumption of being right. His understanding of atomic structure and crystal structure was not merely professional, it was foundational. He had helped build the framework everyone else was working inside. And Linus Pauling had an explanation for Shechtman's photographs that was not a quasicrystal. His explanation was called multiple twinning. And it is worth understanding, at least loosely, what that means, because it is not a foolish idea. Twinning, in crystallography, is a real and well-documented phenomenon. Sometimes, when a crystal grows, 2 or more slightly different orientations of the same underlying periodic crystal join together at a common interface, like 2 separate tiles placed face to face. The resulting structure, a twinned crystal, can look, in a diffraction pattern, as though it has a symmetry it does not actually possess, because you are seeing the superimposed signals of 2 or more differently oriented conventional crystals. Pauling's proposal was that Shechtman's aluminum-manganese alloy was not a single new kind of material with a genuinely forbidden symmetry. Instead, it was a very large, very complex assembly of ordinary crystals, all twinned together in a specific arrangement, and that this twinning was producing the appearance of 5-fold symmetry without the substance of it. A mirage of the impossible, generated by a large and complicated, but ultimately conventional structure. It was a serious scientific proposal. That is important to say. It was not an idle dismissal. Pauling went to work on it, devising successive models of larger and more complicated twinned assemblies to account for Shechtman's data. He was genuinely engaged, genuinely convinced he was right, and he had the mathematical fluency to build plausible versions of his alternative. But he also said something that was not a mathematical model. He said, in a formulation that has been quoted widely enough that it has settled into the record as the signature line of this whole affair, that there is no such thing as quasicrystals. Only quasi-scientists. It is a sharp sentence. You can hear the finality of it, even now, even in a quiet room in the middle of the night. Not quasi-scientists as a gentle jest. As a judgment. As a way of saying that the man reporting these findings was not doing real science, that the work itself was beneath serious consideration, that the error was not merely technical but fundamental, and that the person making it could not be fully trusted to read his own data. Shechtman, for his part, did not respond in kind. He continued doing the work. He continued refining his measurements, gathering more evidence and waiting with a patience that must at some moments have felt more like endurance than serenity, for the world to catch up. And Pauling continued his opposition. Not for a year, not for 2 years. He maintained it until he died in 1994. Right to the end, he was proposing new and ever more elaborate twinning models to avoid conceding that the quasicrystal was a genuinely new thing. The last of those models involved unit cells of almost inconceivable complexity, periodic structures with enormous repeating units, rather than acknowledging that the underlying order was genuinely aperiodic. He was wrong about this, and it cost him, in the long run, nothing except the quiet loss of being the last great holdout on a question the rest of the field had resolved. But in the years when Shechtman was still fighting to be heard, the weight of Pauling's authority was a formidable thing to carry against you. There is something worth sitting with in all of this. It is not a story about ignorance. Pauling was not ignorant. He was brilliant, and his understanding of crystal structure was as deep as anyone's. It is a story about what happens when a genuinely large mind builds a framework so well and understands it so thoroughly that the framework itself becomes the lens through which new information is filtered, and the new information, if it does not fit, gets explained away rather than absorbed. The more authority you carry, the more convincing the explanations you build for anomalies. And the more convincing those explanations are, the longer the anomaly can be held at bay. No rush. Let that rest with you if you like. You can come back to it later, or not at all. The idea will still be here in the morning. What turned the tide was not, ultimately, a more persuasive argument about Shechtman's data. Or not only that. What turned the tide came from a direction nobody would have predicted, from the other side of mathematics, from a field that had nothing to do with metallurgy or diffraction or alloys, from a man who had set out to answer a question that seemed purely abstract, with no connection to the physical world whatsoever. His name was Roger Penrose, and the year was 1974. To understand what Penrose did, you need to think about floors, or rather, about the problem of tiling a floor, covering an infinite flat surface with identical tiles, placed edge to edge, with no gaps and no overlaps. If you have worked with square tiles, you know this is easy. Squares tile perfectly. Rectangles tile perfectly. Regular triangles and regular hexagons tile perfectly. The tile shape repeats in a regular, periodic grid, and the pattern fills the floor as far as you care to extend it. You can always tell, by looking at any patch of a tiled floor, exactly what the pattern will look like somewhere else on that floor, because the whole thing is built from the same repeating unit. But pentagons do not tile. That is not a guess or an opinion, it is geometry. Regular pentagons, placed edge to edge, leave gaps between them that cannot be filled by other pentagons. The angles simply do not add up to fit. And this fact, trivial as it sounds when you are lying in bed thinking about kitchen floors, turns out to carry enormous weight in crystallography. Because the mathematical reason pentagons cannot tile a flat plane is closely related to the reason that five-fold symmetry is forbidden in a periodic crystal. The two ideas are connected at a deep level, and crystallographers had understood this connection well enough that five-fold symmetry was not merely considered unlikely, it was considered provably, geometrically impossible for any real crystal that needed to fill space in an orderly and periodic way. Roger Penrose was not, in 1974, thinking about crystals. He was a mathematician and mathematical physicist, brilliant, unconventional, interested in deep structural questions about space and pattern and order. He was thinking about a different problem. Can you tile an infinite plane using a set of tiles that is governed by strict rules? Rules that determine how tiles may be placed next to each other in such a way that the resulting tiling never ever repeats. An aperiodic tiling. A tiling that covers all of infinite space without gaps or overlaps, but that never settles into a regular repeating pattern. This was not obviously achievable. In fact, for a long time it was an open question whether aperiodic tilings could exist at all with a finite set of tile shapes, especially a small finite set. The first person to prove that they could was a mathematician named Robert Burger in 1966. But Burger's proof required a set of 20,426 distinct tile shapes. It was a proof of existence, not a practical thing. 26 tiles would already feel excessive for a tiling game. 20,000 tiles is a thought experiment, not a construction. Roger Penrose, thinking carefully and beautifully about the problem, found a way to do it with just two tile shapes. In one of the most elegant reductions in modern mathematics, Penrose showed that if you take two specific rhombus shapes, one fat and one thin, meaning one with wider angles and one with narrower ones, and if you follow specific rules about how their edges may be joined, the resulting tiling covers the infinite plane without ever producing a repeating pattern. The tiling is ordered, perfectly, precisely ordered, in the sense that it is completely rule-governed and deterministic. But it never repeats. You can also describe the same tiling using two different shapes, sometimes called kites and darts, which are quadrilaterals that fit together to make the same non-repeating patterns. The shapes look different from the rhombi, but the underlying mathematics is the same. Either way, two shapes, infinite coverage, no repetition. Ever, that last part deserves a moment of appreciation if you can spare one before you drift. The pattern of a Penrose tiling does not repeat after 100 tiles, or 1,000, or 1,000,000,000. Take two patches of the tiling, separated by as much space as you like. They will always look very similar, uncannily similar, because the rules that generate the tiling constrain it so tightly that certain local patterns must recur everywhere. But they will never be identical. You can travel forever across an infinite Penrose tiling, and the pattern you started with will never come back exactly as you left it. The tiling is like a very long piece of music that keeps returning to familiar phrases but never quite plays the same measure twice. And here is the quiet, mathematical miracle that lives inside the Penrose tiling. It has five-fold orientational order. If you look at the directions in which the tiles point, at the orientations of the edges, at the overall geometry of the pattern, you find that everything is organized around 5 preferred directions that are separated from each other by the angles of a regular pentagon. The whole infinite tiling, built from just 2 rhombus shapes, is organized around 5-fold symmetry as precisely and as completely as a snowflake is organized around 6-fold symmetry. Order, 5-fold order, extending across an infinite plane without any repeating unit, without any tile that stamps itself again and again. The pattern is there, everywhere, perfect and consistent, and yet nothing in it repeats. There is also the golden ratio, approximately 1.618, though its decimal expansion, like the tiling itself, never settles into a repeating block of digits. The golden ratio appears in the Penrose tiling in a very concrete way if you count all the fat rhombus tiles in a large Penrose patch and divide that number by the count of thin rhombus tiles in the same patch. The ratio approaches as the patch grows. And as the patch grows to cover the entire infinite plane, the ratio of fat tiles to thin tiles converges exactly to the golden ratio. Not approximately. Exactly, the golden ratio is woven into the tiling the way light is woven into the color of a flame. Not an ornament placed on top, but something that emerges inevitably from the underlying structure. Wherever you go in a Penrose tiling, the golden ratio is there in the proportion of tiles, and the golden ratio is itself connected to five-fold symmetry in a deep geometric way. It appears naturally in the geometry of a regular pentagon, in the ratio of a diagonal to a side, in the proportions that keep coming back whenever you work with five-fold objects. But in 1974, all of this was pure mathematics. Beautiful mathematics. Surprising mathematics. But with no apparent connection to the real world of atoms and alloys and diffraction machines. Roger Penrose published his aperiodic tiling, and it was recognized by mathematicians as a remarkable piece of work, a profound and elegant answer to the tiling question, and the wider world did not pay it much attention. Something else was about to happen, though, a step that would make the bridge visible. In the early 1980s, 1981 and 1982, just as Dan Shechtman was taking his photographs in Gaithersburg, a British crystallographer named Alan Mackay asked a question that nobody, as far as the record shows, had thought to ask before. Mackay was not asking about mathematics for its own sake. He was asking about physics. He was asking what would happen if you placed atoms at the vertices of a Penrose tiling. Not a hypothetical atom, not a toy model, a physically plausible arrangement of atoms sitting at the intersection points of a Penrose lattice. And then, what diffraction pattern would a beam of electrons produce if it passed through that atomic arrangement? This was the question that built the bridge. Mackay worked through the calculation. He took the geometry of the Penrose tiling, placed atoms at its vertices according to the rules the tiling specified, and then computed the Fourier transform, the mathematical operation that tells you what diffraction pattern a given atomic arrangement will produce. It is the same mathematics that underlies how a transmission electron microscope reads a sample, though here it was being done on paper, with a theoretical structure. And the diffraction pattern he calculated from his theoretically imagined Penrose vertex atomic arrangement showed 10-fold symmetry, 10 bright spots arranged in a ring. The same pattern Dan Shechtman would find in his aluminum-manganese alloy. Mackay had, in 1981 and 1982, effectively predicted Shechtman's photograph before Shechtman took it. He had shown that an atomic arrangement built on Penrose tiling geometry would produce exactly the kind of diffraction signature that crystallography said no crystal could produce. He had demonstrated, theoretically, that there was a coherent, mathematical way for a solid to have long-range 5-fold orientational order while still being aperiodic, while still having no repeating unit cell. The rule that forbade 5-fold symmetry applied only to periodic crystals. An aperiodic arrangement, one that was ordered but not periodic, was not forbidden at all. The geometry of the Penrose tiling was, in this sense, the missing piece, not missing from the physics. The physics was sitting on Shechtman's photographic plate, missing from the imagination of the field. Nobody had considered, in any serious and worked-out way, that order could exist without periodicity. The crystallographic restriction theorem did not say order requires repetition as a law of logic. It said that periodicity restricts symmetry to certain types. What Mackay's calculation showed was that if you dropped the requirement of periodicity, if you allowed order without repetition, then the symmetry restriction dissolved. Five-fold symmetry was forbidden to periodic crystals. It was perfectly fine for aperiodic ones. The creature Shechtman had photographed, the creature he said to himself in Hebrew, "There is no such creature," did in fact exist. It was just a creature the textbooks had not imagined, because the textbooks had never seriously entertained the category of ordered but aperiodic. The pentagon that would not tile a floor was only forbidden from tiling a floor with an identical copy of itself beside it, and another one beside that, forever repeating. Penrose's kites and darts had shown, and Mackay's calculation had confirmed. That five-fold order could fill space beautifully, completely, without a single repeating unit, without any gap, without contradiction. It is the kind of resolution that, when you hear it, feels almost obvious in retrospect, the way many of the best solutions do. Of course, order does not require repetition. Of course, you can have a pattern that is perfectly structured, perfectly governed, extending to infinity without ever stamping the same tile down twice. Music does this. Certain mathematical sequences do this. The universe, it turns out, does it in the atomic arrangements of a rapidly cooled aluminum alloy. But before you can see the obvious in retrospect, someone has to do the work of making it visible. Penrose did it with two tiles on an infinite plane. Mackay did it with a calculation that translated the tiles into atoms and the atoms into a diffraction photograph. They had not known they were solving Shechtman's problem. The work was done, at least in Penrose's case, with no thought of crystal physics at all, with the pure intention of understanding the geometry of tiling, the way a craftsman might spend years perfecting a dovetail joint without ever imagining that someone else will use the technique to build a door. And yet the work was there, quietly waiting, when the door needed building. Shechtman, in 1982, did not know about Mackay's calculation. The worlds of mathematical crystallography and the experimental lab at the National Bureau of Standards did not overlap in a way that would have put Mackay's theoretical work on Shechtman's desk. The discovery happened independently of the mathematical framework that would eventually explain it, which is perhaps the most human thing about the whole story. The photograph was taken before anyone had a language to describe what it was showing. The answer was in the camera before the question had been fully asked. And so the 2 silent years began. The diffraction pattern on the photographic plate. The 3 question marks in the notebook. The whisper, "There is no such creature," sitting alongside images that proved the creature was real. And somewhere else in the world, on papers and in calculations that had not yet found their way to him, the mathematical explanation was already complete, waiting to be connected. It would find him. Eventually, things do, when they are true. The path is not always smooth, and the wait is not always short, and the voice that insists on the error sometimes belongs to the most decorated man in the room. But the path finds its way. Linus Pauling was still alive. He was still thinking about multiple twinning, still building his models of large periodic unit cells, still certain, or still claiming certainty, that the forbidden symmetry was an illusion produced by the superimposition of many small conventional crystals seen at once. His opposition was not a whisper. It was the opinion of a double Nobel laureate, published and repeated, and it had the effect that very important opinions in science have. It lengthened the time between the observation and the acceptance. It made the silence heavier. But silence is not permanent. And the data, that stubborn, patient, repeatable, tenfold ring of bright spots, was not going to change itself to accommodate even the most authoritative objections. Shechtman had what he had. He knew what he had seen. And somewhere, in the geometry of two tiles on an infinite plane, the universe had already laid out the mathematics that would make sense of it. The paper was coming. It would take a little longer. And when it arrived, it would not arrive quietly. It would arrive in one of the most prominent physics journals in the world, with 4 names on it, in November of 1984. And it would land in the community like a stone dropped into still water, sending ripples that would not stop until they had reached the definition of the word crystal itself. But that is a step further along the road, and there is no hurry. The mathematics of the Penrose tiling is still here, if you would like to rest with it a little longer. Those 2 tiles, fat and thin, filling their infinite plane without ever settling into a repeat. The golden ratio running through the tile counts, quiet and exact. Alan Mackay's calculation, sitting on paper, the predicted photograph matching the actual photograph. The bridge already built before the person who needed to cross it had even heard that a bridge existed. There is something genuinely peaceful about that, if you let it be peaceful. The universe is not waiting for us to imagine something before it does it. The quasicrystal was not waiting for Roger Penrose to invent the tiling, or for Alan Mackay to run the calculation, or for Dan Shechtman to put the aluminum-manganese alloy under the beam. It was simply being what it was. The mathematics was describing it, not creating it. The fact of the thing preceded all the words and all the arguments, the way the night sky precedes any atlas of stars. The forbidden shape was real. It had always been real, and the work of the years ahead was simply to make the rest of the world see what one quiet scientist in a government lab in Gaithersburg, Maryland, had already seen on a morning in April, with 3 question marks in a notebook and the image of 10 bright points arranged in a ring they had no right to form. No right by the old rules. Anyway, the old rules were about to begin. Very slowly, and with considerable resistance, to change. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. But here is where it gets extraordinary. All of that mathematics, the tiles, the golden ratio, the predicted photograph, was sitting quietly in the literature. A handful of people knew about it. And Dan Shechtman, that April morning in 1982, had his notebook entry and his 10 bright points and his 3 question marks. He had the image. He had looked at it many times. He had rotated the sample. He had confirmed it was not an artifact, not a smear, not a trick of the beam. The pattern was real, and the pattern was forbidden. And those 2 facts were going to have to learn to live with each other somehow. The problem was that nobody wanted to help them do it. So the image sat. The data sat. And for roughly 2 years, while the alloy rested in its sample holder and the notebook stayed in its drawer, the discovery waited for a way into the world. 2 years is a long time in a scientific life. Long enough to grow tired of defending yourself. Long enough to wonder, quietly, in the hours before sleep, whether the instrument had been right and you had been wrong. Shechtman had done everything a careful scientist does. He had checked, and rechecked, and checked again. But the authority of the field was stacked against him, and the most authoritative voice of all, Linus Pauling, was not softening. If anything, Pauling was gathering ammunition. And yet, There were 4 names on the paper that finally made it through. Dan Shechtman, Ilan Blech, Denis Gratias, John W. Kahn. The paper appeared in November 1984 in the journal Physical Review Letters, which is about as prestigious a place as solid-state physics has. The title was precise and unadorned and quietly revolutionary, metallic phase, with long-range orientational order and no translational symmetry. Read that title slowly, because every word in it is doing something. Metallic phase. This was not a theoretical construction. It was a real material, a real alloy, the aluminum-manganese sample that had been sitting under the transmission electron microscope 2.5 years earlier. Long-range orientational order. The atoms were not scattered randomly. They knew which way they were pointing, across vast distances by atomic standards. The long-range order was real and measurable and undeniable. The sharp, discrete diffraction spots were proof of it. No translational symmetry. That last clause is the one that changes everything. Translational symmetry is what a normal crystal has. It means you could pick up the entire crystal, slide it a fixed distance in some direction, and it would look exactly the same. The unit cell, the small repeating box of atoms, tiles the space by moving. And the symmetry of that movement is what crystallographers had built their whole science on. No translational symmetry meant no unit cell, no repeating box, no floor tile that copies itself endlessly in every direction. What the material had was something subtler and stranger, and in its way more beautiful. It had order without repetition. Almost at the same moment the paper appeared, 2 other researchers were arriving at the same destination from the theoretical side. Dov Levine and Paul Steinhardt, yes, the same Paul Steinhardt who would later spend a decade hunting for a natural version of the thing, had been working independently on the mathematics of what a 3-dimensional aperiodic structure might look like, and they gave it its name. Quasicrystal. From quasi-periodic crystal, a crystal that is almost periodic, that has a rhythm like periodicity, that produces order like periodicity, but that never quite settles into the simple repetition that the old definition required. It is a beautiful word, actually, quasi. It carries a sort of modesty. Not quite this, not quite that, a thing at the edge of a category, redefining the category by existing at its edge. Levine and Steinhardt also worked out what the theoretical structure would have to look like in 3 dimensions to produce the diffraction pattern Shechtman had photographed. And the answer was remarkable. The structure had icosahedral symmetry. An icosahedron. Take a moment with that shape if you like. You have almost certainly held one. A 20-faced solid, each face an equilateral triangle. 20 triangles meeting at 12 vertices in a shape that feels, when you turn it in your hands, almost eerily balanced. A die. A virus capsid. The platonic solid that most resembles a sphere without being one. And the icosahedron is riddled with 5-fold axes. 6 of them, in fact, 6 directions through the solid around which you can rotate it by 72 degrees, 1/5 of a full turn, and arrive at an arrangement that looks identical to the one you started with. 6 5-fold rotation axes. The most forbidden case of all, by the crystallographic restriction theorem. The theorem said 5-fold was impossible once, and here was a structure with 6 of them simultaneously. If the crystal had possessed only 4-fold symmetry, the establishment might have quarrelled with the data and moved on. But icosahedral symmetry, 6 5-fold axes in 3 dimensions, was the geometry that most thoroughly and completely violated everything the restriction theorem said could happen. It was not a minor transgression. It was walking into the middle of the room and overturning the table. Let me try to give you a picture of what icosahedral symmetry feels like in an atomic solid, because the abstraction can drift a little if you don't give it something to rest on. Imagine a single atom at the center of a tiny invisible cage. Around it, on the surface of an imaginary sphere, you place 12 atoms, 12 neighbors, at the vertices of an icosahedron. That little cluster has perfect icosahedral symmetry. Now imagine that arrangement propagating outward, each new shell organized around the same underlying five-fold logic, further and further from the center, with no break in the orientational order, each shell oriented consistently with respect to all the others, but never locking into a periodic repeat, never forming the neat translating box that a textbook crystal would have. The orientation runs through the whole material, coherent and precise. The repetition never comes. That is the thing Shechtman's alloy was doing. And there was a one-dimensional way to think about it that helped make the idea a little less alien. Consider the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. You know it, each number the sum of the two before it. Now imagine using that sequence to arrange atoms in a line. Not a periodic line, not the same spacing repeated, but a sequence of two different spacings, call them long and short, arranged in the Fibonacci pattern, long, short, long, long, short, long, short, long, long, short, long, long. The pattern is deterministic. It never repeats exactly. It has long-range order in the sense that knowing the rule tells you everything about the arrangement at any distance. But there is no unit that simply tiles the line by copying itself. That is a one-dimensional quasicrystal, the Fibonacci analog. And the three-dimensional icosahedral structure Shechtman had found was the same idea promoted to 3 dimensions. A periodic in the way a Fibonacci sequence is a periodic, ordered in the way a Fibonacci sequence is ordered. Deterministic, coherent, rule-governed, simply not periodic. The word for what it was had now been said, quasicrystal. The structure had been named, the paper had been published. The theory and the experiment had arrived in the same year from different directions and pointed at the same thing. Now the world had to decide what to do with them. It did not decide quickly. Linus Pauling did not concede. He had never been a man who conceded easily, and on this particular question he dug in with extraordinary tenacity. He spent the remaining decade of his life, he died in 1994, proposing alternative explanations, each one more elaborate than the last. First, large complex unit cells with many atoms, then even larger ones. Then models involving the interpenetration of multiple crystals oriented slightly differently, the multiple twinning hypothesis he had championed from the beginning, but dressed in increasingly elaborate mathematical clothing. The phrase most often attributed to him, treat the exact words gently, as they were reported and recounted rather than transcribed, ran roughly, there is no such thing as quasicrystals, only quasi-scientists. Whoever said those words, in whatever precise form, the sentiment was real, and the target was Shechtman. But here is what was quietly happening in the laboratories while Pauling was arguing. Other people were making quasicrystals. More and more of them, in more and more compositions. And the earliest alloys, the original aluminum-manganese system, had been fragile things, metastable, meaning they existed in a state that wanted to settle into something else, given enough time and heat. Critics could point to that and say there's the problem, it's a defect structure, it's a transitional phase. It's an artifact of the rapid solidification technique. Push it a little and it will resolve into something ordinary, so people pushed it. And some quasicrystals pushed back. The alloy aluminum-copper-iron, Al-Kufay, 3 elements, aluminum and copper and iron, proved to be thermodynamically stable. Not fragile, not metastable, not waiting to collapse into something more conventional. You could heat it, hold it at temperature for extended periods, let it equilibrate, and it would remain a quasicrystal. It was the ground state, not a waypoint to somewhere else. The same was true of aluminum-copper-lithium. Thermodynamic stability was the argument the critics had been holding in reserve. A quasicrystal, they suggested, was a defect, a glitch, a transient configuration that ordinary physics hadn't sorted out yet. Stable quasicrystals demolished that objection. If the structure were a mistake, nature would correct it. Nature did not correct it. The stable quasicrystals sat at room temperature, inert, untroubled, defying the restriction theorem with perfect serenity. The scientific community is not a single mind. It is thousands of individual minds, each updating on evidence at its own pace. Some updated quickly, others slowly, a few not at all, until the end. But the accumulation of stable alloys, the reproducibility of the diffraction patterns across different laboratories using different instruments, the successful theoretical predictions, all of it was doing what evidence does when it is real. It was accumulating. It was not going away. And a reckoning was coming. The reckoning came in 1992. The International Union of Crystallography is the body that, among other things, maintains and updates the formal definitions that the field of crystallography operates by. It is not a dramatic institution. It does not issue press releases or make announcements designed for public consumption. It does the quiet administrative and scientific work of maintaining standards and definitions, and in 1992 it did something that, for anyone who understood what had happened in the preceding decade, was almost shocking in its implications. It changed the definition of a crystal. The old definition, the one that had stood for something like 70 years, said essentially this: a crystal is a solid with a periodically ordered arrangement of atoms. Periodic, the word was baked in. Periodic order was not an optional feature of a crystal, it was definitional. It was what a crystal was. The new definition said something different. A crystal is a solid that produces a discrete diffraction pattern. That's it. That's the whole move. No mention of periodicity, no requirement that atoms repeat in a unit cell. The criterion is purely observational. Shine a beam at the material, and if you get sharp, discrete spots, not a blur, not a smear, but a pattern of distinct points, you have a crystal. Quasicrystals produce sharp, discrete diffraction spots. They had always produced sharp, discrete diffraction spots. Shechtman's photograph from April 1982 had 10 of them in a ring so precise you could use it to calibrate an instrument. Under the old definition, quasicrystals could not exist. Under the new definition, they were simply a different kind of crystal. Aperiodic crystals. Crystals whose long-range order arises from quasiperiodicity rather than periodicity. The textbooks were not wrong, exactly. They were incomplete. They had described all the crystals anyone had ever found and built a theorem around what those crystals had in common. The theorem was airtight, given the assumption. The assumption that every ordered solid is periodic was the thing that broke. And the body that writes the definitions looked at a decade's worth of evidence and did the thing that scientific institutions ideally do, and sometimes actually do. It updated. The definition of a crystal was rewritten. Let that settle, if you can. because it is not a small thing. Definitions are the furniture of a discipline. They are what you arrange the evidence around, the vocabulary inside which experiments are designed and results are interpreted. Changing a fundamental definition is not a correction of an error in the way that correcting a calculation is. It is an admission that the furniture needs rearranging, that the room you thought you understood has a door that nobody saw. In 1982, Shechtman had found that door. In 1984, 4 scientists had published the finding that the door was there. And in 1992, the institution that maintained the room had officially added the door to the floor plan. But there was still one more vindication to come, the one that would be, in its way, the most personal. October 5, 2011, Stockholm, the Royal Swedish Academy of Sciences. The Nobel Prize in Chemistry is announced in October every year, and the announcement is a sparse and formal thing. The name, the institution, the reason, in precise institutional language. The 2011 announcement said, the prize was awarded to Dan Shechtman, of the Technion in Israel, for the discovery of quasicrystals. To Dan Shechtman, alone, not shared, not divided between several researchers who had contributed to the field, to the one person who had put an aluminum-manganese alloy under a transmission electron microscope on the morning of April 8, 1982, who had counted the 10 bright spots, who had written 3 question marks in his notebook, who had said to himself, in Hebrew, Ein haya kazo, there is no such creature, and who had over the following years been handed a textbook by a supervisor, been asked to leave a research group for bringing disgrace upon it, been publicly dismissed by the most decorated structural chemist of the century, and who had continued, with whatever composure that required, to believe in what he had seen. The Academy's statement said that his discovery had fundamentally altered how chemists conceive of solid matter. Fundamentally altered, not adjusted, not refined, not extended, fundamentally altered. There is a particular kind of vindication that only time can produce, and this was it. Not merely being proved right, that had happened in stages, incrementally, across the years. Being proved right loudly, formally by the highest institution in science, with a specific acknowledgement that what you had done was not incremental, that it had changed the foundation. The man who had been told to reread a textbook received the Nobel Prize for having made the textbook wrong. Linus Pauling had died in 1994. He had not lived to see the 1992 redefinition. He had not lived to see the Nobel. He had spent his final years continuing to argue that the twinning models were adequate, that quasicrystals were an artifact, that the crystallographic restriction theorem was intact. He was one of the greatest chemists of the 20th century, and on this particular question he was wrong. And he never knew it with certainty, in the way that a noble announcement makes certainty irresistible. It is worth sitting with that for a moment, not to feel superior to Pauling. It would be a strange and ungenerous response to the career of a man who had done as much for structural chemistry as any person alive. But because it tells you something about how difficult it is to set aside a framework you helped build. Pauling had spent decades working with the crystallographic restriction theorem. He had used periodic atomic structures as the foundation of his most important work. The idea that order and repetition were separable, that an ordered solid could be a periodic, was not merely counter to the evidence as he understood it. It was counter to the very architecture of reasoning that had produced his greatest results. To believe Shechtman, Pauling would have had to take apart a room he had built and loved, and he did not do it. That is not a failure of intelligence, it is a very human thing. And Dan Shechtman, who was by all accounts a patient and not a combative man, had simply waited. Not passively. He had published, he had presented, he had defended his data. But he had not tried to win by force of argument alone. He had let the evidence accumulate. He had let other laboratories make stable quasicrystals. He had let the stable quasicrystals answer the question that no argument could settle as cleanly. Here is a detail worth letting land quietly. After the Nobel announcement, Shechtman was asked in various interviews about the years of rejection. He did not describe them with bitterness. He described them, more or less, as a thing that had happened, a scientific dispute, difficult at times, but one in which the instrument for resolution was always the same: more data, cleaner data, reproducible data, more quasicrystals made by more people, in more compositions, with more instruments. The facts had a way of doing the work, eventually, if you were patient. That is, in a certain light, a more interesting story than a simple tale of genius versus orthodoxy. It is a story about how knowledge actually moves, not in sudden, clean revolutions, but in the accumulated weight of evidence pressing against a framework until the framework has no choice but to accommodate it. The 1992 redefinition was not a moment of drama. Nobody famous said anything quotable. A committee met and altered a definition in institutional language and published it in the appropriate places. But that was the moment the door was officially on the floor plan. So now you know what a quasicrystal is, in the most important sense. Not in the chemical sense. We will come to the specifics of what these materials are actually like, how they behave, what their strange properties amount to, what the structure feels like when you hold a piece of it in your hand. That is still ahead, and it is genuinely interesting, and there is no hurry toward it. But in the most fundamental sense, in the sense that matters most to the history of the idea, a quasicrystal is an object that proved a theorem wrong. Not by finding an error in the logic, but by existing. The theorem was airtight given the assumption was wrong, and the proof of that wrongness was a sample of aluminum-manganese alloy under a beam of electrons on a Tuesday morning in Maryland. And a new category was born. A periodic order. Order without repetition. A kind of structure so counterintuitive that the entire field of crystallography had assumed it was impossible, not because anyone had checked, but because nobody had needed to check. Because nature, as far as any laboratory could tell, had never done it. Except that nature had done it. It turned out that nature had been doing it for a very long time. Longer, in fact, than the Earth itself had existed. But we are not quite there yet. Let the laboratory story finish first. Because there is still the question of what these materials are actually like, and the answer to that question is strange enough to deserve its own unhurried attention. A quasicrystal is, in many ways, an extremely peculiar metal. Most metals, when you think about what makes them useful, are useful because of what their electrons do. Electrons in a metal flow. They carry charge. They carry heat. They respond to electromagnetic fields. They enable the ductility that lets you bend a copper wire or press a sheet of aluminum foil into the shape of a bowl. The periodic lattice of a conventional metallic crystal is what the electrons flow through, and the regularity of that lattice is part of what makes the flow possible. Quasicrystals are metallic alloys. They contain aluminum, copper, iron, manganese, lithium, metals unambiguously, but their electrons do not behave like metal electrons. The aperiodic structure scatters the electrons in a way that an ordinary lattice does not, and the result is that many quasicrystals are remarkably poor conductors of both electricity and heat. Put a quasicrystal next to an ordinary aluminum alloy and measure how well each carries current. The quasicrystal will disappoint you if what you wanted was a conductor. They are also extraordinarily hard. Glass hard by the standards of metallic alloys. The aperiodic structure impedes a phenomenon called dislocation motion, the way atoms in an ordinary metal can slide past each other in organized steps, which is what makes metals bend and deform without shattering. In a quasicrystal, that organized sliding is disrupted by the aperiodicity. There is no regular lattice for the dislocation to glide along. So the material is brittle and resistant to deformation in a way that normal metals are not. And they do not stick to things. This one sounds almost too convenient, like a property assigned for narrative purposes. But it is real. The surfaces of many quasicrystals, particularly the aluminum-copper-iron system, have unusually low surface energy, which means other materials do not adhere to them well. They are non-stick in the way that a very good cooking surface is non-stick, for reasons that trace back all the way to the aperiodic atomic arrangement on the surface. Nothing can quite find a comfortable grip. Combine those three properties, poor thermal conductivity, extreme hardness, low surface adhesion, and you have something genuinely unusual. A material that resists heat transfer, resists scratching, and resists sticking. Those are not properties you typically find together in a single material, and they are not properties that metallic alloys were known to offer before quasicrystals were found to exist. The applications that followed from those properties are real, though many of them are still being explored and refined. Coatings based on aluminum-copper-iron have been developed for surfaces that need to resist wear, resist corrosion, and not accumulate residue. The logic is straightforward. If you want a coating that will protect a surface and not accumulate material on it over time, the combination of hardness and low adhesion is exactly what you need. And then there is the steel. A Swedish company called Sandvik, a manufacturer known for precision tools and materials at the demanding end of the performance spectrum, developed a miraging-type steel that uses quasicrystalline precipitates within its microstructure to achieve exceptional hardness. The quasicrystal particles are not the bulk material in this case, they are tiny inclusions within the steel, strengthening it the way rebar strengthens concrete. And the products that steel is used for are not abstract, surgical needles, razor blades, instrument components. Objects that need to be precisely shaped, extremely hard, and reliable under conditions that would dull or deform a lesser material. That is the quasicrystal, made useful. Not in the laboratory, not in a journal paper, but in a surgical suite, in a razor held against a cheek on an ordinary morning, in the instruments that perform the small precise acts that medicine requires. The creature that could not exist, making itself useful. There are other directions the research has gone: thermoelectric materials, hydrogen storage, thermal barrier coatings, solar absorbers. And many of those directions are still very much research stage, not settled applications. The quasicrystal's combination of low thermal conductivity with a specific electronic structure makes it potentially interesting for thermoelectrics, devices that convert a temperature gradient into electrical current, or vice versa. The mathematics of how that conversion works in an aperiodic structure is still being worked out. The promise is real, the delivery is ongoing. But there is a limit to how deeply you need to follow the applications tonight. You are not here to write a materials specification. You are here for the shape of the story. And the shape of the story has one more turn in it that no application or property list can match. Because all of these quasicrystals, Shechtman's original aluminum-manganese, the stable aluminum-copper-iron, the aluminum-copper-lithium, the alloys tested in hundreds of laboratories around the world, all of them had been made by human hands, by instruments, by crucibles, by rapidly solidified melts, by carefully designed synthesis conditions. As far as anyone knew, quasicrystals were a laboratory achievement, a thing that required a transmission electron microscope and a carefully controlled process to produce. The natural world, it appeared, had missed the trick. Rocks and minerals and the long geological processes of the Earth had been laying down crystals for billions of years and had somehow never stumbled onto quasiperiodic order. Or so everyone assumed. Paul Steinhardt was not so sure. Steinhardt, who had coined the word quasicrystal with Dov Levine in 1984, who had spent the subsequent years building out the theory, who had watched the field grow from a contested novelty into a recognized category of matter, Steinhardt had a question that would not let him rest. If quasicrystals were stable, if they were thermodynamically favorable in the right compositions, if nature routinely produces whatever configurations of atoms are available to it under the right conditions, why hadn't nature made one? Or had it? The hunt he launched, and where it led him, is the part of this story that takes place not in a laboratory in Maryland or a journal office in New York, but in a storage drawer in Florence, and in the mountains of a far eastern peninsula of Russia, and in a meteorite that had been travelling through space for 4.5 billion years. That is the part that is still ahead. For now, let the laboratory chapter close at the moment it deserves to close, October 5th, 2011, a name spoken in Stockholm, a prize awarded to a single scientist for a discovery that had been declared impossible and that had turned out to be real and true and important enough to force a rewriting of definitions and old enough to have been quietly present in the universe since long before there. Was anyone here to be surprised by it? Dan Shechtman, the discovery of quasicrystals. The man with the 3 question marks in his notebook had the answer, it turned out. The universe had simply taken a while to tell the rest of the world, so the laboratory chapter was closed. But the question Steinhardt carried was not the kind that closes with a Nobel citation or a ceremony or a press release. It was quieter than that, more personal. The kind of question a scientist carries home and sets on the table and finds still sitting there in the morning, untouched, if nature makes whatever it can make. If the conditions are right and the chemistry is favorable and the atoms have time and energy enough, then nature should have made a quasicrystal somewhere, at some point. In the 4.5 billion years this planet has existed. The stable alloys had been found in the laboratory. The theory was sound. The thermodynamics permitted it, and nature, as a general rule, does not politely wait for humans to give it permission. So where was the natural one? Steinhardt began looking, not casually, not as a side project. He looked seriously and systematically, and he looked for a long time. The hunt would eventually consume the better part of a decade. The first challenge was knowing where to look. Natural minerals are not catalogued by their diffraction patterns. They are catalogued by their composition, their colour, their hardness, their lustre, their place of discovery. A quasicrystal would not advertise itself with a label. It would sit in a drawer or on a shelf, collected years or decades earlier for some ordinary mineralogical reason. its strange internal geometry entirely unannounced. Steinhardt and his collaborators began searching through published records of mineral compositions, looking for anything with the right chemistry. The synthetic quasicrystals he knew best included aluminum combined with copper and iron, or aluminum with copper and lithium in the right proportions. So he looked for natural minerals that might contain the same elements in similar ratios. Rare combinations. Unusual alloys. And then, in 2009, something turned up. The something was a grain, a very small grain, a fragment of rock that had found its way, through a series of purchases and transfers and the ordinary migrations of mineral collections, into the holdings of the Natural History section of the University of Florence, in Italy. A museum drawer in Florence. A grain so small you would need a microscope to see it properly, sitting in a sample labelled with the kind of quiet, dry descriptor that museum mineral records use, a metallic fragment from a carbonaceous chondrite. Steinhardt's collaborator in this phase of the hunt was a mineralogist named Luca Bindi. Bindi worked at the University of Florence, and it was Bindi who examined the grain and found that its composition matched what Steinhardt was looking for, approximately 63% aluminum, 24% copper, 13% iron. Al 63 Cu 24 Fe 13, the same family as the stable quasicrystalline alloys that had been synthesized in laboratories since the late 1980s. They subjected the grain to electron diffraction. They looked at the spots. Tenfold. Icosahedral symmetry. Sharp, discrete diffraction peaks, arranged with the very pattern that had stared out of Shechtman's notebook photograph in 1982. It was a quasicrystal, not made in any laboratory, not produced by any human process, a natural one. The conformation took time, the grain was tiny and precious, and they handled it with the care due something that might be genuinely unique. But the analysis held. The mineral was real, its symmetry was icosahedral. Its internal structure had the long-range order and the aperiodic arrangement that defined the quasicrystalline state. In 2010, the International Mineralogical Association formally recognized it as a new mineral. They gave it a name, icosahedrite, named for the icosahedron, the 20-faced solid whose symmetry it bears. Composition Al 63 Cu 24 Fe 13. The first quasicrystal ever admitted as a legitimate mineral in the official record. But there was still the question of where it had come from. Carbonaceous chondrites are a class of meteorite, some of the oldest and most chemically primitive rocks in the solar system, remnants of the debris that existed before the planets formed. But which meteorite? And from where? The trail, with patience, led to the Katerka meteorite, a CV3 carbonaceous chondrite. That classification, CV3, places it among a group of meteorites thought to have originated in the asteroid belt, fragments of a parent body disrupted long ago. The 3 indicates a relatively low degree of thermal alteration, which means the rock has preserved something close to its original chemistry. And the name Katerka pointed toward a location. The Koryak Mountains. Far eastern Russia. The Chukotka region, one of the most remote and difficult territories in the world, a landscape of tundra and permafrost and jagged terrain in the far northeastern corner of the Asian continent, where it reaches toward Alaska across the Bering Strait. In 2011, Steinhardt's team mounted a field expedition to find it. This is worth letting settle for a moment, because it is not the part of the story you would expect. a theoretical physicist and a group of colleagues, following a paper trail from a museum drawer in Florence to the end of the world, looking for fragments of a rock that had fallen from the sky. They found them. In the Koryak Mountains, in that remote landscape, they recovered further meteorite fragments, and those fragments contained quasicrystalline grains, the same icosahedral structure, the same icosahedrite composition. The match confirmed what the museum grain had suggested: the natural quasicrystal had arrived on Earth from space. Now hold that for a moment. The Katerka meteorite is approximately 4.5 billion years old. That age, 4.5 billion years, places its formation at or near the very beginning of the solar system. The sun had just ignited. The planets were still assembling from clouds of gas and dust and rock. The Earth had not yet fully formed. Life would not appear here for another billion years or more. And somewhere in that ancient chaos, in the asteroid belt or in a collision between early solar system bodies, a quasicrystal was made. The impossible crystal, the configuration that every textbook of the 20th century had declared forbidden for a periodic solid, had existed in nature since before the Earth had oceans, since before there were any eyes to see it, or any laboratories to dismiss it, or any textbooks to declare it impossible. Nature, working with the raw materials of a young solar system, had found its way to the aperiodic order, to the icosahedral symmetry, to the long-range arrangement without repetition, entirely on its own. Steinhardt's question had been answered, and the answer was, in its quiet way, extraordinary. But how? How does a quasicrystal form in space? There is a clue in the chemistry. Metallic aluminum in its pure elemental form, bonded to copper and iron but not oxidized, is nearly impossible in ordinary nature on Earth. Aluminum is the most abundant metal in the Earth's crust, but it almost never appears in metallic form because it reacts so readily with oxygen. The aluminum you recognize, the foil, the cans, the aircraft parts, all of it is refined from oxide ores through industrial processes that didn't exist before the 19th century. But the Katerka meteorite contains metallic aluminum, bonded with copper and iron in the icosahedrite composition, not oxidized into the minerals you'd expect. For aluminum to survive in metallic form, the conditions of formation must have excluded oxygen almost entirely, and they must have been violent and brief, a rapid process that locked the metal into its structure before it could react. The best explanation the evidence supports is impact. A hypervelocity collision between asteroids, the kind of event that releases energy in fractions of a second, generates pressures measured in gigapascals, creates temperatures hotter than the surface of the sun at the shock front, and then cools almost as fast. Under those conditions, extreme pressure, extreme temperature. A chemistry starved of oxygen, the right combination of aluminum, copper and iron, squeezed together at enormous speed, can form the quasicrystalline arrangement. And the rapid cooling locks it in before the atoms have time to rearrange into anything more conventional. The universe, in other words, had access to a synthesis route that no terrestrial laboratory could easily replicate. Not a gentle crystallization from a cooling melt, but a violent shock, the collision of worlds, the physics of impact craters translated to the atomic scale, and out of that violence, a perfectly ordered, beautifully symmetric, aperiodic structure. And the Katerka meteorite held more than one. A second natural quasicrystal was subsequently identified in the same meteorite. This one had tenfold symmetry rather than icosahedral symmetry. Its composition was different, approximately 71% aluminum, 24% nickel, 5% iron. Al 71 Ni 24 Fe5, the International Mineralogical Association accepted it as a new mineral in turn. Its name, decagonite. From the decagon, the 10-sided polygon whose symmetry it echoes, 2 quasicrystals, from 1 meteorite. Both arrived here from the early solar system, travelling through space for 4.5 billion years, resting in the Koryak Mountains until a field expedition dug them up. Both bearing symmetries that classical crystallography had spent decades calling impossible. It is hard not to feel something when you hold all of that together. Not awe in a dramatic sense, something quieter. A kind of recalibration of scale. The argument that it had never been observed in nature rested, it turned out, on the fact that we hadn't looked in the right place. The right place was 4.5 billion years back in time and a very long way from any university campus. Let's stay with the material for a little longer, because there is something genuinely strange about what quasicrystals are like as objects, not as mathematical abstractions, but as physical things you could hold, or coat a pan with, or use to make a surgical needle. Remember that quasicrystals are metallic alloys, aluminum-copper-iron, aluminum-copper-lithium, various compositions in that family. You would expect metallic properties, good conductivity, some ductility, the ability to deform under stress. That is, after all, what metals do. The shared electrons move freely, carrying heat and electricity. The atomic planes slip past each other under load, which is why you can bend a wire without it shattering. Quasicrystals do almost none of this. They are extremely poor conductors of both electricity and heat. For a metal, this is remarkable. The aperiodic arrangement of atoms disrupts the smooth passage of electrons in ways that a regular crystal lattice does not. Electrons moving through a quasicrystal scatter at every step. There is no long repeating highway for them to travel along, only an irregular landscape that sends them sideways. The result is low electrical conductivity, low thermal conductivity. Numbers that look more like a semiconductor or a ceramic than a metal. They are also very hard. Not in the way that hardened steel is hard, through a microstructure of carbides and martensitic phases, but glass-hard, brittle. Push them far enough and they fracture rather than deform. Again, the reason lies in the aperiodic structure. In a normal metal, plastic deformation works through dislocations, defects in the crystal lattice that can glide along specific crystallographic planes, allowing layers of atoms to slip past each other relatively easily. This is why metals are ductile. Quasicrystals have no periodic lattice planes along which dislocations can glide cleanly. The aperiodic arrangement impedes dislocation motion. The structure that makes them so unusual also makes them resistant to the mechanism by which ordinary metals give way. And there is one more property that sits alongside the low conductivity and the hardness, and it is perhaps the most practically interesting of the three. Quasicrystals have very low surface friction and very low wettability. They are, in a word that oversimplifies but captures the idea, quite remarkably non-stick. Water and oils and many other fluids bead up on their surfaces rather than spreading. Things slide across them rather than gripping. This is a peculiar combination. A material that is metallic in composition but ceramic-like in conductivity and hardness, and non-stick in surface behavior. You would not design this material from first principles. You would not expect it. And yet here it is, dictated entirely by the mathematics of a periodic order. The practical question, naturally, is whether that combination is useful. It is, in some specific ways. The aluminum-copper-iron quasicrystalline composition, Al-Q-Fe, essentially the same family as icosahedrite, has been developed into wear-resistant, low-friction coatings. The hardness protects surfaces. The low friction reduces wear. The low wettability repels oils and moisture. These coatings have been studied for applications that need surfaces to last under stress without corroding or accumulating deposits. The most striking application in actual commercial use comes from a different direction. A Swedish company called Sandvik developed a maraging-type steel, a high-performance steel that incorporates quasicrystalline precipitates within its microstructure. The quasicrystal particles are distributed through the steel in tiny inclusions, and those inclusions harden the material in ways that conventional carbide particles cannot match quite as precisely. The result is steel of exceptional hardness and edge-holding ability. What is that steel used for? Among other things, surgical needles, and razor blades, and precision instrument components, things that need to be exceptionally sharp, exceptionally hard, and exceptionally resistant to wear. In those applications, the quasicrystalline precipitates, those tiny pockets of a periodic order embedded in an otherwise conventional steel matrix, do real, practical work. They make the needle sharper. They keep the blade keener, longer. There is something pleasingly strange about that. The structure that crystallography declared impossible, that spent 2 years unpublished, that Linus Pauling dismissed until his death, that structure is, among its other achievements, making surgical needles sharper. Other applications have been explored with varying degrees of success and proximity to commercial use. The low thermal conductivity of quasicrystals makes them interesting as thermal barrier coatings, materials applied to surfaces that need to insulate against heat. The combination of low electrical and thermal conductivity, with a particular relationship between the two, makes them candidates for thermoelectric applications, devices that convert a temperature difference into an electrical voltage, or vice versa. Hydrogen storage is another area of research. These are largely still in the investigative phase, rather than routine production. But the investigation is real and ongoing. The field that Shechtman's 3 question marks opened in 1982 has grown into a genuine subdiscipline of materials science, with its own journals and conferences and graduate programs and industrial partnerships. Thousands of quasicrystalline compositions have now been synthesized. Their properties have been measured, modeled, and argued about. The structure that didn't fit any existing category has generated its own category, with its own extensive literature. And before the final turn of this story, the turn toward wonder, toward the view from a long distance, there is one more thread to pull. It belongs not to a laboratory or a meteorite, but to a wall. A very old wall, in a city that was a centre of art and mathematics and architecture at a time when the European continent was still finding its way out of the medieval period. Isfahan, Iran, the year 1453. A shrine called the Darb-e-Imam was decorated in the 15th century with a tiling pattern of extraordinary complexity. The craftsman who built it used a set of 5 decorated tile shapes, tiles that Islamic architects had been using for several centuries, known as giri tiles. Giri means knot in Persian. The 5 shapes, a regular decagon, a regular pentagon, a bow-tie hexagon, an elongated hexagon, and a rhombus, could be assembled into elaborate geometric patterns covering large surfaces. What the builders of the Darb-e-Imam created on those walls in Isfahan was not a simple repeating pattern. It was something much stranger and, in retrospect, much more remarkable. In 2007, physicists Peter Liu and Paul Steinhardt, yes, the same Steinhardt, published an analysis in the journal Science showing that the Darby-Imam tiling, along with several other examples of 15th century Islamic architectural decoration, exhibited the same structural properties as a Penrose tiling. The arrangement of tiles was aperiodic. The long-range orientational order was there. The pattern had five-fold symmetry at large scales and never exactly repeated. The builders in 1453 were not working from anything that resembled Penrose's 1974 mathematical analysis. They almost certainly did not know in any theoretical sense what they were doing. They were following a set of practical rules about which tile shapes fit together, guided by an aesthetic tradition that prized complex geometric harmony and an evident mastery of the visual grammar of their tile system, and yet the patterns they produced by following those rules had the property that Penrose would formalize in a different language 5 centuries later. The property that Shechtman's diffraction photograph would demonstrate in a metal in 1982. The aperiodic order. The non-repeating pattern that nonetheless holds together at all scales. This is not mysticism. It is not a claim that the craftsmen of Isfahan secretly knew quantum physics or had access to 20 first-century mathematics. It is a claim about the tile shapes themselves, that the set of Giri tiles, with their specific angles and proportions, enforces quasi-periodic order when you follow the fitting rules carefully enough. The mathematics was latent in the geometry. The builders found it empirically through generations of practice before anyone had the algebraic language to describe it. Peter Liu and Paul Steinhardt described it as evidence that medieval Islamic architects had independently developed through practical geometry, a technique that produces quasi-crystalline tiling, roughly 5 centuries before Penrose formalized the mathematics, and roughly 5.5 centuries before Shechtman found the physical structure in a metal. So the pattern was there in 1453 on a wall in Iran. It was in Penrose's calculations in 1974. It was in Shechtman's diffraction photograph in 1982. It was in the Katurka meteorite for 4.5 billion years before any of those dates. The same deep geometric truth, approached from different directions, from human aesthetic practice, from abstract mathematics, from electron microscopy, from the physics of asteroid collisions, and arriving each time at the same place. Order without repetition. Let me say that simply, one more time, because it is the thing this whole long night has been slowly approaching. Order without repetition. For most of the history of crystallography, and before crystallography existed, for most of the history of human intuition about the material world, those two things were assumed to come together. An ordered structure was a repeating structure. If something was arranged with precision and regularity, that arrangement had to cycle, had to have a unit that recurred, had to be periodic. The idea that something could be thoroughly, globally, perfectly ordered and yet never repeat, that was not just counterintuitive. It was codified as impossible, built into the crystallographic restriction theorem, written into textbooks, enforced as a rule that nature itself was supposed to obey. And then a photograph showed 10 bright spots in a ring. And then 2 tiles covered an infinite floor without ever repeating. And then a meteorite 4.5 billion years old contained the forbidden pattern, arrived from the early solar system, formed in the shock of worlds colliding. What the quasicrystal revealed, slowly, through 2 years of unpublished data and decades of opposition and a Nobel Prize given to one man alone, is that order and repetition are not the same thing. They were always separate, It was only our models of the world that had joined them, and the joining was so deep and so old that it felt like reality rather than a model. The textbooks were not wrong because they were careless or lazy. They were wrong in the way that useful models become wrong by being too useful for too long. A model that works beautifully within its domain eventually gets mistaken for a description of all domains. The crystallographic restriction theorem is a true and rigorous result for periodic structures. The error was not in the theorem. The error was in assuming that all ordered structures must be periodic, a logical step too far. A universe assumed to be narrower than it is. Shechtman's 3 question marks were not just the record of a man doubting his own measurement. They were, looking back, the record of a moment when reality declined to fit the theory. Not with a dramatic bang. Not with a confrontation or an argument. With 10 bright points in a ring on a Tuesday morning in April 1982, in a government laboratory in Maryland, in a diffraction pattern from an aluminum-manganese alloy that nobody had thought particularly special before he put it under the microscope. The universe had simply been waiting for someone to look. And lying there in whatever comfortable darkness you've arranged around yourself tonight, there is something in this story that goes a little beyond the chemistry and the crystallography. Something that is, I think, genuinely worth carrying into sleep. The hardest thing to see is the assumption so fundamental you don't know it's there. The crystallographers weren't failing to notice the theorem, they were failing to notice what the theorem assumed. The assumption that all ordered matter must be periodic was so deep it had ceased to look like an assumption. It looked like a fact about nature. It looked like the way things are. And this happens, quietly, in every domain of thought. Not just in crystallography. Every field, every discipline, every institution, every way of seeing carries assumptions built so deep that they look like descriptions of reality rather than choices about how to describe it. They go unexamined not because anyone is negligent, but because the framework they support works too well for the examination to feel necessary. It takes something like a photograph of 10 bright spots. Something that just doesn't fit. Something that sits in a notebook with 3 question marks next to it, unpublished for 2 years, while the most famous chemist in the world explains it away, waiting patiently for the world to catch up. And here is what I find most settling about this story on a slow night like this one. The thing that was declared impossible was real all along. Not almost real. Not approximately real. Real and ordered and beautiful and patient. It was in a museum drawer in Florence. It was in a meteorite in the Koryak Mountains. It was on a wall in Isfahan in 1453. It was in the asteroid belt 4.5 billion years ago, crystallizing from the shock of colliding worlds. All that time, the quasicrystal was simply there, waiting to be named. The naming took until 1984. The Nobel took until 2011. The meteorite hunt took until 2011. The recognition of the Giri tiles took until 2007. None of it happened quickly. All of it happened eventually. Evidence, in the end, is more patient than authority. There is something restful in that. Not triumphant, there is no villain in this story, really, not even Pauling, who was simply applying the best framework available to him with the full force of his formidable intelligence. There is no triumph, except the quiet one of a thing being true, and eventually being seen to be true. Order without repetition. It was always there, we just needed the right microscope, pointed at the right alloy, by the right person, on the right morning. A person willing to write 3 question marks, rather than explain the result away. Wherever you are right now, Whatever the hour is in your corner of the world, you are lying somewhere in a universe that turns out to be more spacious than its textbooks once described. A universe that accommodates arrangements nobody predicted. A universe that had been building quasicrystals in asteroid collisions since before the Earth had a surface to stand on, entirely indifferent to whether or not the humans who would eventually arrive had a theoretical framework ready to receive them. That is a large thing to carry, but it is also, somehow, a light one. If you are still awake, I am glad you stayed through the whole journey. The forbidden photograph, and the 2 silent years, and the man asked to leave his research group, and the tiles that tile without repeating, and the grain in the museum drawer, and the mountains of Chukotka, and the meteorite 4.5 billion years old. All of it. And if you drifted off somewhere in the middle, somewhere in the Penrose tiles, maybe, or on the plains of the early solar system, that is perfectly fine too. The quasicrystal will still be there when you wake up. The icosahedrite will still be in its mineral drawer, recognized and named and legitimately real. Shechtman's notebook will still have its 3 question marks. The textbooks will still have been rewritten. Order without repetition. That idea is yours to keep. If you enjoyed this slow journey tonight, a gentle like or subscribe helps this sleepy little channel more than you might think. Small creators like me rely on your support to keep these journeys going. And I would love to know, where in the world are you listening from, and what time is it in your corner of the night? Leave it in the comments when you wake. Sleep well, fellow voyager. The next journey keeps until you wake.